This is part 2 of the wind load tutorial. This part is going to look at diaphragm and brace loads using figure I7. So the first example says we have a 2-story building located in Burlington, Saskatchewan. We're given the pressure for that region. It's a normal importance building in open terrain, and we're told to find the wind loads for diaphragm and brace design. So this is another situation where we're looking at main structural action, so this is why we're using figure I7, and we have a low-rise building. So here I don't have to worry about internal pressure because I'm looking at the diaphragm and brace design, so the internal pressures would cancel out, so I'm just going to look at the external pressures. And so this is our formula. We have our RW value, our Q value, and our CE value, which are given here. For the CPCG values, as we mentioned, we're going to have to use figure I7. Okay, so I've set up a table here. It gives you the different CPCG values. So you have the windward side, so that's region 1, and the leeward side, region 4, and you can calculate the pressure using the formula that we showed above. So in this example, I'm also including N regions. So if you look at the figure, if you look in the figure, you have these regions of additional load. It goes to that figure right here. So these regions here are called N regions. They're going to experience additional load. So this region here, 1E and 4E, is going to have extra load. So if you look here, instead of 0.75, we're going to have a 1.15 value. And for region 4E, instead of minus 0.5, it's minus 0.8. Okay, so you need to use these. So that's what I included in the table. This is the N region in the windward side and the N region in the leeward side. And you can find the pressure for that. The next thing you're going to need is, what is this distance? What's this N region distance? Right? What is this value Y? So for this, you need to look at footnote 6. Okay, so with all these figures, and you should read these footnotes for all these figures because they have important information. If you look at footnote 6, it tells you how to calculate this. So I'll let you read this, but in summary, what's this value Y? Y is equal to the maximum of 6 meter, or this other value 2Z, where Z is equal to the minimum of 10% of B, which is your minimum planned dimension, or 0.4 H, and also Z has to be bigger, equal to 4% of B, or 1 meter. So these are lower limits. So if you go through all this, you're going to find the value that's going to control is this 6 meter. So basically this region here, almost up to the column, is an N region. So this is N region here, and the rest is your regular region. So if I'm looking at wind blowing like that, this would be 1, and this would 1E, and this would be region 1. And over here I'd have region 4E, and beyond this I have region 4. Okay, so that's important. So this is going to be important when I'm going to find the forces. So this is the summary of the pressures I found for each of these regions, and this is 1E, region 1, region 4E, and region 4. Remember, when you have a negative value, that means it's pulling away from the surface, and this is why I'm showing the arrows like that. Okay, now what I need to do is transfer this pressure, because I have now a pressure which is acting on this entire roof surface, this wall surface, right? I took the windward and the leeward side. I'm going to have pressure which is acting on this surface. So what I want to do is transfer this pressure onto point loads like this at the column locations, which are going to transfer to my diaphragm. So I have forces on my roof level, and I also have forces on my floor level. So I'm going to find these values, and the way I find it is just based on the tributary area concept. So let me just use a different color here to distinguish between the end region and our regular region. So I'm just using this to distinguish between this. Okay, so what I need to do is look at my tributary area. So for example, for this column, it's in region 1, so that's why I'm going to use 0.34, and then the tributary area is just, I go halfway to the next columns. Okay, so that's my width over here is is 6.5 meters. Okay, so I'm going to go halfway to the next column, and then I go halfway down to the floor. Okay, so that's my tributary area for this column. So for example, for region 1, how did I get this 4.97 kilonewtons? I just took the 0.34 kilopascal, and then I multiplied by 6.5 times the interstory height divided by 2, which is 4.5 over 2, and I find this 4.97 kilonewton. So that's for this column and this column, these two loads over here. For this one, which is in the corner, this is again in region 1, but it's in the corner. So instead of having 6.5 width, you're going to have 6.5 over 2 width. And so that's why I'm going to use half of the region 1 value. So that's 2.49 kilonewton. If I look at this column over here, this column is in region 1E. So I should use the 0.52 kPa, but the tributary area in this case is equal to 6.5 over 2 multiplied by 4.5 over 2. So that's what I have over here, and I'd find 3.81 kilonewton. The last column I have is this one over here. So this column over here. You can see this column, part of its tributary area is in region 1 and part of it is in region 1E. So what I'm going to do is I'm just going to take the average of the region 1 value and the region 1E value. And so that's what I'm doing here. I'm just taking the average of these two. This 7.62 is just the regular 1E value, so it's double this value here. So I take the average and I find 6.29. So that's for the windward side. For the leeward side, it's the exact same thing, except I use the leeward pressures over here. Okay, so this is for the roof. For the floor, it's the exact same thing. So we have the same pressures, except now the tributary area is just double, right? Because instead of just having, like if I look at this column, the tributary area now is the same width, it's 6.5 meters, but now you have double. You have 4.5 over 2 from the top and 4.5 over 2 from the bottom. So that's why these values are just double what I have up here. So these are the values here. So once I have this, I can show the diaphragm forces at the roof level and at the floor level. And then there's another step, which is the actual diaphragm design. So this I can model like a simply supported beam, and I could find the shear diagram and moment diagram, and these values, those shear values and moment values, I would use to design, for example, the connection between the deck and the beams and so on, to ensure I have proper design. Similarly, I can use these forces to find what my brace loads are. So if I look at my building, I have a braced bay over here. Okay, so that's the system that's used in this building. We have a braced bay over here. So what are the forces coming on these braced bays? I can find it using these diaphragm forces I found. Okay, so at the roof level, I can just find the force going into my brace, which I can call RW here, and for the other side RE. So this is for east and for the west. So if I look at this and I just take the sum of moments about this value here, I can find what my force is, and I find it's 21 kilonewton. Same thing for the floor level. If I take some forces, some moments about here, I'm going to find the value here, which is 42 kilonewton. You'll notice the west value is bigger than the east value, and that's because we have the N region over here. So when I'm doing design, I should consider this 21 kilonewton for both the west and the east, because the N region can be here and it can also be here. So this is an important point. You should consider 21 kilonewton. You should not consider this 18 for the east value as well. So once I have this, I can put the forces over here, and then this is my system. It's an X brace system, and here we're going to design as a tension only brace system. So when the forces are coming here, this value, this ones that I showed in green, is going to be in compression, so we're going to assume they buckle and they don't contribute. So it's a tension only system, and I can find the forces in my brace just by doing a truss analysis. And then I should consider wind going in the other direction. So now these ones will be in compression, and so we're gonna ignore them, and then I can find my different forces in my brace, and I can use this for design. After we've determined these concentrated loads on my diaphragm on both surfaces and also these reactions, I can look, for example, at this roof diaphragm and draw a shear moment diagram for this. So using, for example, the roof loading, I can draw this shear diagram and this moment diagram. And if I consider wind going in the other direction, then I could actually draw a shear envelope and a moment envelope. And then you can read this here. This would be used for designing the diaphragm decking and its connections for these loadings. The other thing is you have chord members in this diagram. So if I'm looking at this loading, this would act as a deep beam over here, and what you can think about is this here is in compression, this here is in tension. We call these elements along these edges chord members. So you have compression chord members and tension chord members. From this moment diagram, so we've determined these moments here, we can find the force in these chords just by using this simple equation: moment is equal force times the depth of the building. And so you can use that and find these forces. So that's what they're doing here. So for example, here is the tension forces. You would also consider compression forces as well. Okay, so you can read the details here, but that's how we would find the loading on our diaphragm. Okay, here's another example for a single-story building. It's in Ottawa, Ontario, normal importance, open terrain, and we're told to find the wind loads for diaphragm and brace design. So exact same thing, except we have a single-story building. So we go through the same steps. We set up our CPCG table, we find our pressures, and then we distribute our loads to our columns. So again, these here are not floors, these are wind girts. So don't get confused by that. This is just a single-story building. So for example, if I look at this column here, I just need to use the tributary area for this column, and I could find the point load over here. So I can do that, and I can find it in region 1, in the corner of region 1, and in region 1E, and in the corner of region 1E, and at the first interior column where you have this average that I mentioned. So if you do this, you're going to find these forces on the windward side. Just for your information, here's the E region, and here is 1, this is 1E, this is 1, this is 4, and this is 4E, and here's your intermediate column. Okay, so this is your intermediate column right here, your first interior. This is 1 is here, the 9.2, and the 6.6 over here. Once we've determined these point load forces which are acting on the diaphragm, we can also determine the forces which are acting on these brace bays. So you can see here they find a value here of 73.2 kilonewton. So what they do is, first, the building is symmetric, so shear center coincides with geometric center. So the shear center of the building is here in the middle, and what they'll do is they'll take the sum of forces from here and here, you add this up, you end up with 139 kilonewton. And what we're gonna do next is, because of the unbalanced loading, right here you have some end regions, and so the loading is a bit unbalanced, and so what's gonna happen is that resultant is not gonna act right in the shear center, not right in the middle of the building. So you can find this eccentricity, and if you do that, you'll find it's 2.28 meters. And then with this resultant, this eccentricity, and these point loads, you can determine the forces on each of the braces. So on this side, on the other side, and even on these perpendicular sides. Okay, so you can read the details here. So what you need to do is you need to put this resultant at this eccentricity, and then you can use these equations here to find the forces on each of the braces. And what you'll find is more force goes into this brace than this brace, and in fact some limited force is also going to go into these braces, because what's going to happen, you're going to have a bit of torsion in your building. So when you're designing this, the largest force is going to be on this one. So you design your brace base for the force on this one, and what can happen, this eccentricity can be on the other side, right? The end region can be on the other side, and so the same load you would use to design this brace as well. Okay, so you can read the details here. It explains how they do this. In addition to this, what we can do is we can, just like in the previous example, we can draw a shear diagram and a moment diagram for our diaphragm design, and we can consider our diaphragm here just as a deep beam. Okay, so we can use the shear forces to design our steel decking and its details. So the thickness of that decking, the connections, everything would be, we'd look at the shear diagram. And then for the moment diagram, we can use that as well to determine the forces in these collector elements in the compression and tension phase. Okay, so you can read this here. They'll talk about this here. If you read this, just like the calculation we saw in the previous example, they're going to take that moment, divide by the depth of your diaphragm, you get the forces in your collectors. Okay, so you can look at that for more detail.